Hello everyone, last video I've been demonstrating an update on a bare minimum Go playing program in JavaScript that I've written not very long time ago. And this time I'd like to show you a derivative project called MicroGo. So this is the tiny Go Weiqi Baduk playing program with a GTP interface this time. So I wanted to translate my program into C programming language, make it as tight as possible, and to see how it would be performing with a deeper search as opposed to JavaScript because C is faster. So this video I'm going to show you the end result of this work. So since this is the GTP interface, we need a GUI to run it under. Also need to compile it. So yeah, only for those nerds likes programming, likes compiling things. It would be probably not very easy to compile on Windows, but on Linux it should be fine. Although it should be possible on Windows as well. So yeah, if you want to try it, if you want to get familiar with what the hell is this, it's better to use the JavaScript version that you can play directly in the web browser just by navigating the link. Try to play here. You may choose the specific board size and go here, but this is JavaScript. JavaScript is not as fast, so and also JavaScript version involves the GUI, which takes extra space for code. But this kind of thing is very tiny. So before I show you how it plays, I want to demonstrate the source code. So the entire source code is only this 48 lines of code. Well, in C, essentially, the program might be a single line of code. Anyway, so these 3 lines are the variable definitions. Here we have the board string as like defined statements in C. So opening moves, those squares it would take when it has nothing else to do in the opening, when there are no fighting moves. Generally, overall strategy is if you have a group with less than 3 liberties, try to use eninge max search to recursively to a given depth. I'm using depth of 6 here to find some fighting moves to either avoid getting captured or try to capture the group on your own, on computer's own. Another type of moves are known as tanuki. Tanuki means play away. So this program will be trying to find a group of your stones and try to surround this group of stones with its own stones. The idea behind this is to make it possible that engine will essentially play a complete game of Go. Yeah, and also if user does something very bad, then engine would win automatically because just attaching to a group of stones would eventually result in just grabbing more territories. So yeah, probably the right thing to say is I'm not satisfied because the way how it plays is not very good. But assuming the amount of source code, only this one, I think this is quite cool. So let's break down. So from line 35 and down below, all this is just GTP protocol, so the text protocol, so that the GUI can communicate with this program via text commands. So hopefully that makes sense. So these 3 lines are the variables the program is using to work. Then starting from here and up to here, this is the implementation of the entire rule set of the game of Go, including the rule of co. So this is probably the most interesting part. And again, just to get it more clear how it works, you just have a look at JavaScript version. Syntax of C and JavaScript is fairly similar. So I understand it might be hard to understand what's going on here, but essentially just these 4 main routines. So count liberties populates 2 arrays, the array of the group array and the liberty array. G is the group array, L is the liberty array. And it's used for various purposes. It's used for within the heuristics of how to play the move. say to find the forcing moves, we need to find all the groups, we need to count all the liberties. Those group that has less than 3 liberties would be marked as the moves to loop over during the search. So that's one of the applications. Another application of count is used when it comes to capturing the group of stones, removing this from the internal board, from the inner board. The inner board is B. It's string. It could have been represented just as an array, but just to make it possible to print a board by a single printf statement, I made it string. And this comes with some extra complications, like we need to do some additional math to turn the contents of a square on a board into somewhat an integer value because those are characters by default. So yeah, comes with a price. This routine, next one, R, means restore board. So after we count liberties, the values of stones are being changed. The values of empty squares that do represent liberties are also being masked with some different values. So we need to make some cleanups after, so that we make sure that our position is not going to be messed up. Then this one, this particular one is used to implement the rule of Ko. So if you have a square in a diamond, so like upwards we have a stone, downwards we have a stone, to the left we have a stone, and to the right we have a stone. And if those stones are of the same color, this would return true, otherwise it would return false. So this is used to implement the rule of Ko in the game of Go. Then the next one, this P, it's the set stone routine. So it sets the stone on board, and if it happens that capture occurs, it would remove the stones from board. Also checks out for move legality, like not to play the move on a square marked as co-square, and also avoid suicide moves. So if you have the group with only 1 liberty left, if you put a stone there, it would be like a self-capture, so this is not allowed. So to avoid that sort of a scenario, this function would also check for that situation, and would return 1 if the move is legal, and would return 0 if the move is not legal. We'll also change this site, this one. Okay, then the AI part itself is this function called x. So essentially what it does is quite simple. So if we hit the depth of 0, so it's called with a depth of 6, that's the value I came up with. Well, via trial and error method, I would say. So essentially what the static evaluation does, it does one single thing. It just calculates all the white squares, all the white stones and all the black stones, and whoever has more stones has the better static evaluation. This is that simple. So if you capture the group, the amount of stones left on board would be different. So the group that has captured the group of opponent stones would have more stones. So this is very likely like capturing pieces in chess. So very simple evaluation. Since this is an Eggmax framework, the score return would be plausible for black and the negative value for white. Then we go into the main search routine, so starting with the best score minus infinity. Then this array U would contain those moves to loop over during the search. Again, those moves to loop over during the search would be those moves when we found groups where the number of liberties is less than 3. All those liberties would be traversed during the search. But it also might happen that there are too many. Say if you are capturing an opponent into a ladder or getting captured into a ladder by computer, it starts getting extremely laggy with no particular benefit for the playing strength. So we just limit, if we have more than 6 14 squares to calculate, then we just make it 6. So if we have less, then we have less. This is fine. So we just limit the search. We're not searching all the possibilities. We just search the first 6, essentially. This may eventually lead to blunders, but again, since this is about to be encountered mostly only during like ladders, still this is like practically this is more or less just fine. Okay, then quite probably one of the things that I really like is that we can preserve the board state by the single string copy routine. Okay, so this is the benefit of having the board representation as a string, so we can just do the string copy. And then when we make a move, then we can, if we find a better score, so we only store the best move for the root nodes. Then we just elegantly restore the board position over the side to move and also co-square if available. And we return the best score eventually. If there are no forcing moves in the position, or if this condition is met where we just abandon some liberties to avoid our engine searching forever, then another option is Tanuki, also known as play away move. So essentially, all these 3 lines of code do, they just try to find a group. They just try to find the group. Excuse me. Oh no, this is not. Just try to find a group and try to surround the group. But it might happen that you may consider the computer may consider a suicide move. So to avoid this, we have a slight condition. So if we have the liberties more than 2, so these are the type of groups to surround. Those have more than 2 liberties, because those groups that has less than 2 liberties would be calculated within the recursive search anyway. And for those groups having more than 2 liberties, we just initialize the attack variable with the value of liberties array indexed by 0, essentially the very first liberty. Then we just restore the board here, okay? And we make sure that if attack is available, if there is a liberty to fulfill, and if count is equal to at least 1, which means after we place a stone, we are not going to end up with a suicide move, not going to do a self-capture. In this case, we make best move equal to this attack, essentially the first liberty of the first group being encountered. So it would be just going group by group until it fills all the liberties. So essentially, if you do nothing, if there is no tactical complications on board, say you just try to place stones on board edge. This doesn't make sense from the perspective of the game of Go, but just to check it out how this works, it would be trying to essentially surround your group. And once your group has less than 3 liberties, it would try to recursively find the way how to capture a group. That's it. So yeah, essentially this is it. And this one of the biggest functions essentially, just the GTP protocol implementation. So just a very basic commands: the name, engine name, version, protocol version. Without these commands, GUI refuses to work with an engine. Show board is used for debugging. It's very nice. We can print the board in a single printf statement. This is the printf statement. We print the board and decide to move. Clear board also is quite cool. We just do the string copy to initialize the board array with the G is the empty board string. We set the side to black, co, and the best move to empty, and we tell the GUI that we're ready. Generate move does the following. So it passes the user input. It reveals the side to move, whether black or white, and then it resets the best move. Then it calls the search recursively. Yeah, just have some extra spaces that we don't quite need. Calls the search recursively, and if the best score, here I can do some improvement. I may ask if the best move is not equal to 0. Yeah, I just realized that I can try to run another experiment. Okay, so it will either try to play the move found by the recursive search if it's available. Otherwise, if it's not available, it will try to make the Tanuki move. And after this, if after making Tanuki, the best move is not available, it would just simply pause. It might happen that the program will pause a few times, and then it would just play again. So this is also possible, right? And if it's not passed, if there is the best move available, then you just play this move on board. That's it. And this part is to get the row and column from the square. Okay, so just some passing routines. And yeah, the best move that has been returned would be just a square index. So we need to uh, extract the row and the column of that square index, and then we need to turn them to algebraic notation coordinates like A19, for instance, and then we want to print that. So these two lines replace a huge lookup array of, say, huge lookup array of mapping the square indices to coordinates. Yeah. And this one play, it does a bit of the opposite. So it passes user input from the algebraic notation to the square index eventually. And after this, when you have the square index, is calculated by row multiplied by board size plus column. And then decide to move, which is also taken from the user input, might be white, then letter 8, black, then letter 8, and white, then letter B. Not very intuitive, but it works. And yeah, and it then just makes a move on board. Finally quit, just to quit the program. So let's compile and run, and I can do name, I can do version, I can do protocol version. So all those commands, sorry, I'll have to complete here for sure. Okay, and I can do show board. So now this is the empty board. I can do play, say black Q16, then show board, it played. Then I can do gen move for white. It does the move. Then I do show board again, just to have an idea where it has played. Okay, gen move white. Did I play with? I did. I did with the wrong case. Sorry. So let's do it again. I did the wrong case. So play black capital Q16 and then gen move white and show board. Yeah. Now we have black stone and we have the white stone. Yeah, because it's case sensitive. Okay, let's have a look how this beast works in a Sabaki GUI then. So this is it. So in Sabaki GUI, I just need to specify the path to the engine executable, no matter the operating system. It's really similar. So this is the path to where it lives. Okay. And since I only have the only mode, like GTP protocol, so I don't need to specify any additional options to it. So let's say it would be playing as white. Okay, and let's just start a game. So it would start to make some moves that what to play here. Some Fusaki moves, predefined moves. So it's just a lookup database, sort of. It's not pretty much thinking about things. When there would be only two liberty, it stops making opening moves. It starts calculating. So it plays the move to avoid being captured. Although, as a human player, I can beat this program easily. But anyway, just want to give you an idea. So yeah, I just tries to surround me if he has nothing else to do, which is interesting. Yeah, so yeah, I think he already. Oh, yeah. Okay. Here. Now he was going. If I do nothing, he would capture this group. I can probably demonstrate you this, just to give you an idea. So he has captured me. Now he's doing quite good. Okay. I probably want to still make a living group here. This program knows absolutely nothing about eyes and living shape. It's not about that. So it would eventually come up with the living shape somehow, or it may die also. Sometimes it makes weird moves like this, which is the downside of the simple implementation. Yeah, sometimes it would be trying to contribute to a DAG group. But on the other hand, if you have a group with only one eye, this might be crucial, so it may lead to computer killing your group. But anyway, you just have a look at this wall. So if we have a look at the score estimation here, so it's like white is essentially leading by half a point at the moment, quite surprisingly. So, yeah, if I don't play that hard, if I do some not very clever moves, okay, like this, I just want to give him a chance. He would be trying to surround me. So this is like good thing for sure. So, right, he's going to capture this one stone, probably. Yeah, he does that. I cannot recapture because of Co. So, yeah, let's grab this one. Okay. He is absolutely blind to this kind of thing, so he doesn't know he gets surrounded, as well as here. Yeah, by the time I want to, yeah. Okay, so it keeps surrounding. So now if we have a look at territory estimation, like black is still winning. Yeah, I really hope that he would just surround this center. Just want to show you its best, the best options it can come up with, really. And then I will show you how easily it can be smashed. So yeah, let's just do some weird, stupid moves. I just want to give him a chance to. You see, like what he does, he surrounds. He essentially attaches. He surrounds in my groups. Try to surround my groups. But meanwhile, this naturally leads to creating some territory. Okay. Oh, he's trying to take this one. Okay, I give you this. Take this one. Good. This is good. Take this one. Are you going to capture me? Nope. Okay. I'll probably cut this stone out. Yeah, this is not going to live. I think, could he kill me there? I'm not sure. Yeah, I just really want to give him a chance. Maybe I should give him this. No, it's too much. Okay. Okay, defense. I could have play a peep here. And he would not realize that he needs to connect, otherwise he would lose the full stones, but I would not be that brutal. So let's make some stupid move, like trying to give him more chance. Okay, trying to give him more chance. Okay, he still connects. Yeah, I just really want to show what good things he can do. Assuming the tiny amount of code that we have, yeah, so unfortunately, sometimes this like weird moves are happening quite often. So yeah, that's the downside. That is the downside. But if he connects in here, he would be leading the game, I believe. I believe he would be leading the game. Yeah, when he runs out of places where to put the stones. Unfortunately, it's so stupid. Yeah. Okay, he passes because he doesn't know what to do. Okay. Again, he passes, he doesn't know what to do. Yeah, this is the bad thing for sure. Okay. This is the bad thing. Okay. I just want to force it to kind of yeah, sometimes it plays, it's very, very stupid. He should have tried to surround from Like this group, for instance, here. Sometimes it's not working. Yeah, I need to. Does it only go from this side? I'm not sure. Okay, just want to give him a chance to. Okay, he connects. Great. Okay. Yeah, this is so unfortunate. Is he really going to? Okay, maybe. Yeah, maybe. Just want him to complete the. Yeah. Okay. They're going to complete. Okay. Okay. He's not completing the territories. Yeah, finally he does complete the territory. Can you believe? Can you believe? Probably even with this stupid play, I still won the game. Did I? Yeah, no, I didn't. Y plus 49.5. So the game could have been finished at this moment, but just to give you an idea that, yeah, as a human player, if you know what to do, you have all the chances to create a living group where normally you would never be capable of doing that. So just want to quickly demonstrate. Although if he would kill me here, I would be very surprised. Yeah, he gives me all the chances. Okay, now I have a living group, and he passes. Okay, I can keep playing here. I can keep playing, and I can obviously I can crush, smash. So this one, and here, because if it didn't do this, I would have taken this. This is bigger. So yeah, for beginners, it might be quite fun. Yeah, he's doing passes when he doesn't know what to do. Yeah, probably because of being disappointed with the result of this project, I cannot force myself to debug it more to make it like, you know, to make it attaching when, like, instead of passing, try to make it attaching. Yeah, I'm just so disappointed that I cannot make myself doing that, really, to be honest. So yeah, so I'm about to destroy his territory completely. This is that. And I just be greedy and just trying to destroy everything here. Okay, now the top group should be dead soon. Yeah. Yeah, he contributes to a dark group because he's just because of the recursive search. He's trying to escape. Okay, he doesn't know anything about two eyes, so he's not trying to save this. He only has one eye. I will now kill it. So yeah, just to give an idea how stupid this is. Yeah, fortunately, and I just kill. I think I can kill everything if I want to. Yeah, I think I can kill everything here. So that you don't have any illusion like that it might be good. Okay. Yeah, I can play a bit of Go. Can play a bit of Go. But yeah, not very satisfying. So now let's kill this one. Okay. And so on and so forth. Yeah, I think now everything is absolutely dead and can no longer be saved. So I think we can stop over in here. But a few moves ago, say, yeah, you just stopped here somewhere. Then here, Y kind of wins the game. So as I said, it's capable of completing a game of Go. Oh, even though it does passes. And again, just I'm sorry, guys. I'm just so disappointed with the project that I don't really want to spend time on debugging this. Like, so that I can always attach. Yeah, because it's the problem of to always attach. It's the problem of liberties. So if you force it to attach every time, even if there is only one liberty or something like that, then it would be making illegal moves, trying to make illegal moves. So thinking about how to make it a bit different way. I'm just so disappointed, and to be honest, I got sick and tired of this. So I just wanted to show you the end result as is, because the valuable thing here, I believe that the valuable thing here is the source code, not the source code itself, but that all the rules of the game of Go are essentially implemented over in here. So this is the entire rule set, including the rule of Go. So this is quite accurate. And yeah, AI part is just a kind of placeholder. And the rest is the GTP communication. So yeah, simple and straightforward. But not good enough, in my personal opinion, not good enough for it does not deserve to live, maybe not enough to live. Might be cool, but totally useless, utterly useless, unfortunately. Yeah, guys, this is from my side. So you do judge this project if you like. If you have something to tell me about this, please kindly let me know in the commentary. This is from my side. Thanks for watching. I'll see you in the next video. Until then, and cheers.